Chapter 18 is on electrochemistry. So what is electrochemistry? We can use oxidation-reduction reactions and electron transfer to basically create electricity from chemistry. So the flow of electrons is what electricity is. And so research into this flow of electrons from chemical reactions is used in developing cheaper, more efficient ways of generating electricity. So fuel cells, batteries, that sort of thing. Like I mentioned, oxidation-reduction reactions are where electrons are transferred from one atom to another. The short name for that is a redox reaction. The definition is that atoms that lose electrons are being oxidized, and atoms that gain electrons are being reduced. One way to remember it is through the acronym OIL-RIG. Oxidation is loss, reduction is gain. The other one that I like is Leo the lion says GER. So lose electron oxidation, gain electron reduction. That way just makes more sense in my head, but it's up to you which one, or use neither, just memorize it. So my example reaction here, 2 sodium atoms plus chlorine gas go to 2 sodium chloride. So the sodium loses an electron, so that's oxidation. The chlorine gains an electron, that's reduction. When we're looking at more complex reactions, we often assign oxidation states and then look at the change in oxidation state to figure out what's oxidized and what's reduced. So here's a review of the rules for assigning oxidation states. This was back in chapter 4 of your textbook if you want to look at that. And they are in order of priority. Free elements are assigned an oxidation state of 0. Monoatomic ions have an oxidation state equal to their charge. When you add up oxidation states for all of the atoms in a compound, it needs to equal 0. Or if you're looking at a polyatomic ion, the sum of the oxidation states adds up to the charge on the ion. Then when we're looking at compounds, group 1 metals have an oxidation state of +1. Group 1 is the alkali metals. Group 2 metals have an oxidation state of +2. That's the alkaline earth metals. And then rule 5 here is really the one that most of those other ones are pretty intuitive. This table here is kind of the key for assigning oxidation states in molecules. So in their compounds, non-metals have oxidation states according to the priorities here. Fluorine is assigned an oxidation state of -1. Hydrogen is assigned an oxidation state of +1. Oxygen is assigned an oxidation state of -2. Then group 7A, which is the rest of the halogens, is assigned -2. Group 6A, which is the rest of the group under oxygen, is assigned a -2. Group 5A, which is nitrogen and below that, is assigned a -3. So my example here of ammonia, technically the hydrogen is assigned a +1 for all of those, and then nitrogen needs a -3 in order for the sum of them to be a 0, which is the charge on the molecule. So remember that charge on the molecule rule as well. So let's work through this example. Determine the oxidation states of all the atoms in a propanoate ion. Propanoate is C3H5O2-. So our sum of everything needs to be a -1. If we look back at that table, rule 5, our hydrogens are assigned a +1, so my total there is +5 because there are 5 of them. My oxygen is assigned a -2, so that gets me a -4 in total for my oxygens. So my 5 minus 4 plus my carbons is equal to a -1. So that gets me plus 5 minus 4 plus 1 plus whatever my carbon is equal to -1. So my carbon total is -2. If you follow the math, I have 3 carbons. So each individual carbon is that -2 divided by 3. Now, oxidation states, unlike most things in chemistry, can be a fraction. So my total for my carbons was -2. I have 3 of them, so each individual carbon has an oxidation state of -2/3. So this is just working through that, what I just did on the last slide. All right, here's a practice for you. Assign an oxidation state to each element in the following. So here's some for you to work through. I would pause it and then come back and check. So bromine is an atom, so it's 0. Potassium +1 has a +1. Lithium is a +1. Fluorine is a -1. CO2, my oxygen, is a -2, which means my carbon overall is a +4. Here my oxygens are assigned a -2. There are 4 of them. My overall charge needs to be a -2, so my sulfur gets a +6, which came from the -2 times 4 is -8. It needs to add up to -2, so that gets me a +6. Here my sodium is assigned a +1, which means this is the rare case where oxygen is not -2 because the sodium takes priority. It's assigned a -1. So there's that all worked out for you. All right, oxidation-reduction reactions. In addition to oxidation losing electrons, reduction gaining electrons, oxidation, also another way to look at it, is when an atom's oxidation state increases during a reaction. So here our carbon has a -4, carbon and carbon dioxide is a +4, so it's increased, so it's been oxidized. Our oxygen went from a 0 to a -2, and so our oxygen was reduced because our oxidation state decreased. Oxidation and reduction need to occur simultaneously. The electrons need to go somewhere. A couple more definitions for you. The reactant that reduces an element in another reactant is called the reducing agent, or you can look at it as the reducing agent will contain the element that's oxidized. The reactant that oxidizes an element in another reactant is called the oxidizing agent. It's going to contain the element that is reduced. So in our sodium plus chlorine makes sodium chloride. The sodium is oxidized, the chlorine is reduced. Sodium is the reducing agent. It's acting to do the reducing of the chlorine, and chlorine is the oxidizing agent. It's acting on the sodium to oxidize it. Here's a couple tables of common oxidizing agents and common reducing agents. Let me go back one. Notice oxygen is an oxidizing agent. It's going to oxidize other things. It itself will be reduced. One more practice. Assign oxidation states, determine the element oxidized and reduced, and determine the oxidizing agent and reducing agent in the following reaction. So here I would recommend pausing and then coming back for the explanation or checking the next slide to see if you got it right. So iron as an element has an oxidation state of 0. This manganese oxygen compound here, oxygen is assigned a -2. We need to add up to -1, so my manganese is a +7. The 4H plus is a +1. My iron 3 is a plus 3. My manganese oxide here, oxygen is still a minus 2, but my manganese is now a plus 4. And in water, it's minus 2 and plus 1 for my hydrogen. So you can see my oxygen and my hydrogen did not change oxidation state. I'm worried about my iron and my manganese. So my iron here went from a 0 to a plus 3, so it's oxidized. You can also look at it as it lost electrons. My manganese, manganese, therefore is reduced. So the manganese is also my oxidizing agent because it acted to oxidize my iron, and my iron is my reducing agent. Yep, that's everything. So there's the answer.